Okay, everybody, we're going to look at the direct comparison test for convergence and the limit comparison test for convergence here. All right, some examples coming up. So as a reminder, for the direct comparison test, if you're given two series, all right, the summation of one sequence we'll call A sub n, and the summation of another one, the infinite sum of another one, we'll call B sub n, where important, the terms in each are positive. All right, but the terms in A sub n are less than or equal to those of B sub n. All that means is that the corresponding terms in A are less than that of the sequence of B. The first term in A is less than or equal to the first term of B. The second term in A is less than or equal to the second term in B, so on and so forth, okay? So then, if the series of the B sequence converges, then so will the series of the A sequence, all right? And basically what it's just saying here is that if the larger infinite series converges on some value, then the smaller one will also. All right, and then kind of conversely here, if the smaller series diverges, if A sub n diverges, then the series given by B sub n will also diverge. So if the smaller series, if we know that that goes off to infinity, and we have this other series that's larger, then that's going to have to go off to infinity as well by comparison, okay? Now, one thing we got to be careful of is if the smaller series converges, it does not mean that the larger one does. Okay, there's no way to know that. And if the larger one diverges, it does not mean that the smaller one diverges. That, again, we don't know. We got to look into it some other way. All right, but let's do a couple examples and see where this takes us. So first up, we have the series from 1 to infinity of 1 over n cubed plus 7. So the trick to using the comparison test is to, have an understanding of what to compare it to. And it's usually going to be a p-series, a harmonic, geometric, okay, something along those lines, okay. Usually what you can do is if you look at, like, in the case we have here, 1 over n cubed plus 7, if I simply get rid of the plus 7, and I just kind of look at the highest power that's in the denominator there, I get 1 over n cubed, which is a p-series, all right. So that's what we're going to compare this to, all right. So if we look at the terms of this, n cubed plus 7, we're going to compare it to 1 over n cubed. Now, what do we know about 1 over n cubed? Well, this itself is a convergent p-series, all right? So if we can show that the terms of the given sequence are less than or equal to the terms of a convergent p-series, we'll know that our series is going to converge as well, right? All right, so the only difference between these two things is the denominator, right? So here in our denominator, we have a plus 7, and in that denominator, it's just n cubed, right? Well, since the only difference is in the denominator here, think about what's going on. If the denominator here is a little bit larger, what's going to happen to the value of that fraction compared to this fraction? Well, if you start playing around with some numbers, plugging in like 1, 2, and 3 for n, you'll notice that the fraction on the left is actually a little smaller than the one on the right. Right? If we divide by a larger number, which is the case with this particular series, we're going to have a fraction whose value is actually a little bit smaller. So since we have a larger denominator, we know that this fraction in value is going to be less than or equal to 1 over n cubed. All right, and so by the direct comparison test, our series converges. Okay, if we know a larger one, this guy is going to converge, and we can show that these terms are less than or equal to all the terms in the other, then ours is going to have to converge as well. No idea what it converges to necessarily, just that it's going to have to follow suit. All right, let's try another one. Okay, next up, summation as n goes from 1 to infinity of quantity 4n plus 1 over 3n to the nth power. So again, to kind of get a rough sense of what I want to compare it to, I'll start by dropping the plus 1. All right, if I do that, we get 4n over 3n, right? Now we could simplify that. The n's are going to drop off, and this just becomes 4 over 3. Let's not forget the nth power, right? We get 4 over 3 to the nth power. All right, well, that looks like a geometric series, r to the nth power. Well, 4/3 is bigger than 1, right? We know that if the absolute value of r for a geometric series is less than 1, it'll converge. If it's greater than 1, it will not, right? So in this case, we have an R value of 4/3. This would be a divergent geometric series. All right, so if we can show that our given series is greater in value term for term than this one, then we can make the claim that if the smaller one diverges, well, then our series is going to have to diverge as well. So looking up here, we just got to come up with the inequality, if possible, between this and 4/3 to the nth, which we know diverges. Again, we can look at it in this form. Maybe it's a little easier to make the comparison here. Okay, both of those to the nth power. Now, the only difference between these two is that this has a larger value in the numerator. And if we make the numerator a little bit bigger, we make the value of the fraction a little bit bigger. So that's enough to show that that's greater than or equal to the divergent geometric series. And since our series is larger, then therefore, by the direct comparison test, this series, right, this guy that we started with over here, diverges. All right, that's the idea, okay? So, it's a matter of comparing it usually to a p-series or a geometric series. Typically, harmonic shows up as well. Let's keep looking here. Okay, in the next case, we have infinite series, n plus 5 over n cubed plus 7. So again, what I'll do is I'll drop those constants just to get a sense of what this is equal to. And if I simplify that even further, we're looking at what? 1 over n squared. So again, we have a p-series. Since p is greater than 1, 2, right? This thing's going to converge. So we have a convergent p-series that we want to compare to. So again, the idea is if we can show that ours is less than or equal to this convergent series, that'll be enough to say that this one's going to converge as well. So let's take a look. So again, the question is, can we make an inequality between this and 1 over n squared? Okay, again, I'm just going to use this form of it. And now we got to look at what's going on both in the numerator and the denominator. In the denominator, this has a larger denominator when we add that 7. So that's typically going to bring down the value of the fraction. But at the same time, in the numerator, we're adding something, right? So that usually brings up the value of the fraction. So unlike in the previous two cases, in this case, it's kind of hard to see, exactly whether and for what values of n, this sequence that we're given, this series we're given, is greater than or equal to the 1 over n squared that we're comparing it to, all right? So we can't just use the direct comparison test in a case like this. Okay, so this is where the limit comparison test would be appropriate to use. Okay, so as a reminder, the limit comparison test, again, given two series, the terms in A less than or equal to the terms in B, let C equal the limit as n goes to infinity of A sub n divided by B sub n. Okay, or let it be the limit as n goes to infinity of B sub n divided by A sub n. What that means is it doesn't really matter which way you set this up, okay? You can do original over the one you're comparing it to, or you can do the one you're comparing it to divided by the original. It's not really going to make much of a difference, okay? But as long as we get, the important thing is that if C, the limit, right, if we get some positive finite number back, right, some positive number that's not infinity, okay, then both series do the same thing. So if we know what the one we're comparing it to does, if we know that diverges, then we know this other one that we're working with does as well. And same goes for convergence. All right, so let's take a look. So we already determined we can't really tell the inequality here. Okay, but we do know that we're comparing this to n over n cubed, which is 1 over n squared. Now this, again, we know is a convergent p-series. Okay, so let's apply the limit here. We're going to look at the limit as n goes to infinity of, I usually just do the hours, right, the one in question, divided by the one we're comparing it to. Okay, and now what I'm going to do is I'm going to clean this up. I don't like dividing by the fraction here, so keep the numerator one, keep the part up top, and then flip and multiply. Okay, and if we see look at what's going on here, Basically up top, I'm going to have a 1n cubed when I multiply. Down below, I'm going to have a 1n cubed. So I have n cubed over n cubed. As n goes to infinity, I have the same power on top and bottom. N cubed over n cubed is just a coefficient of 1. So this limit approaches 1. Okay, what does that mean? Well, we got a positive number back, right? Didn't go off to infinity. So therefore, right, we got a positive number back, and the one we're comparing it to converges. So therefore, by the limit comparison test, both series do the same thing, which in this case is converge. Okay, so some students ask, can I just use the limit comparison test? Do I have to go through the direct comparison test first? I don't know honestly if there's a correct answer to that. Usually the limit comparison test is going to work if the direct comparison test works, but to use the limit comparison test, you still have to compare it to something. So why not take a couple seconds to see if you can figure out the inequality, and then you're done. If the right one exists. And then if not, roll into the limit, but up to you. Let's take a look at a couple more. All right, series 1 to infinity, 3n squared minus n over 8n cubed plus n. So, in the numerator, 3n squared is going to get really, really large and take over. So I'm going to drop the minus n. And in the denominator, 8n cubed is going to get really large compared to n, so I'll drop the n. Basically, we just look at the highest power terms. And if I clean this up a little bit, we're looking at what? 3 over 8n. All right, that's just 3/8 of 1 over n. All right, well, this is a divergent harmonic. All right, that's the harmonic series, okay? So intuitively, I would think that this is also going to diverge, but let's see. Let's see, first of all, can we come up with a comparison or an inequality here, okay, with this? And again, I just like using that form to compare it to. Now, let's see. In the numerator, we're subtracting an n. And when we make the numerator smaller, we usually make this fraction smaller. At the same time, we're making the denominator larger, which again makes this fraction smaller. So here we can actually make a direct comparison. All right. So it looks like our series, term for term, will be less than or equal to the one we're comparing it to. All right. Oh, well, unfortunately, that doesn't help us because this is a divergent harmonic. So just because the larger one diverges doesn't mean the smaller one does. Okay, so while we were able to make an inequality, it's kind of inconclusive in terms of the direct comparison test. Okay, so what we do now, we look at the limit comparison test instead. So now we'll go limit as n goes to infinity. Here's our original one. Right, and we're dividing it by the one we're comparing it to. So I'm going to kind of cut to the chase here and keep change flip, so to speak. Okay, so I divided by 3 over 8x, and I flipped and I multiplied. Again, if I look at, oops, not x, n, excuse me. Okay, and now if I look at the highest power on top and bottom, up top we're going to have 24n cubed. Down below, we're going to have 24n cubed. So again, this limit happens to approach 1. It happens to be a value I find that we get a lot, okay, just with some of the examples we do. But hey, it's a positive number, and so therefore both, I should say by the limit comparison test, both series do the same thing, which in this case is diverge. Okay. So again, we tried to set up the direct comparison test. It was inconclusive. We moved on to the next one. Okay, a couple more here. Okay, here we're going to drop the plus 3, and we're going to have 2 to the n over 5 to the n that we're comparing to, which can be written as 2/5 to the n power. Okay, that is a geometric series. R is between -1 and 1, so this is a convergent geometric. All right, so let's see if we can again set up the inequality. The only difference is our series has a larger denominator, which means it will be less than or equal to the other one. Okay, And let's see if if this one converges, and the smaller one's going to have to converge as well. So this time by the direct comparison test, our series converges. Okay. Okay, next up. Here we're going to drop everything but the highest power terms, and that's going to become 4 over 7n, which is a divergent harmonic. Remember, n to the first power in the denominator there. All right, so let's see. Can we come up with a comparison? I don't know. There's a lot going on. You know, I'll leave it like that. This has a larger numerator, which makes the fraction larger. At the same time, it has a larger denominator, which makes the fraction smaller. So I think that it's hard to really say concretely without looking too deeply into it, what the inequality is here. Okay, so I'm not going to worry about it. What I'll do is I'll run the limit comparison test. So limit n goes to infinity. Again, it's hours divided by the one we're comparing it to. You're usually dividing fractions, so I'm kind of in the habit of, skipping to the chase here and multiplying by the reciprocal and focusing again on the highest powered terms on top and bottom. Now up top, we've got 28 n to the third. Down below, we've got 28 n to the third. So again, this limit approaches 1. Okay, so by direct comparison test, because we have a positive finite number for our limit, both series do what? Diverge here. Okay. Okay, I think I got 2 more examples for us, okay? Hang in there. This is good stuff. All right, next up, sine squared over n cubed. Okay, so the trick to this one, as n goes from 1 to infinity, is knowing what to compare it to, okay? We're actually going to compare it to 1 over n cubed. So let's look at this. Sine squared of n over n cubed compared to 1 over n cubed. Any guesses? We can actually figure out this inequality, okay? Let's talk about the sine function. What do we know? Well, we know that sine is always between what 2 values? Of course, -1 and +1. If I were to square this, all right, careful. Think about what inequality we will get back now. Well, if I square 1 on the right, I get 1. If I square -1 on the left, I get 1. But sine squared is not always between 1 and 1, okay? So this might have to take a little bit of thinking about, but it actually ends up being that sine squared, if sine is between -1 and +1, sine squared will be between 0 and 1. Think about it. If sine is like -1/4, when you square that, what do you get back, right? +1 over 16, right? If sine is -1/2 and you square that, you get back what? +1 over 4. Okay, if sine is -0.9 and you square that, you're looking at +0.81. Okay, so that's the idea. If sine is between -1 and 1, then sine squared will be between 0 and 1. Okay, so think about what this implies then to our series, right? The numerator of our series on the left is always going to be somewhere between 0 and 1. So the numerator of our series is always less than or equal to the numerator of the series we're comparing it to. So our series is going to be less than or equal. And so by the direct comparison test, our series, well, again, the bigger one converges, convergent P series, so our series converges. Okay. And in the last one, we have a factorial here down in the denominator. Notice we're indexing this at 4, okay? And there's a reason for that, okay? If we look at n factorial for different values of n real quick, okay? Remember, 0 factorial is 1. 1 factorial is 1. 2 is 2 times 1. 3 is 3 times 2 times 1 is 6. That's going to be 24. I'll go one more. 24 times 5 is 120. Okay, and so on and so forth. Okay, but you'll see why we look at that in just a second. So in any event, we've got 1 over n factorial. What can we compare that to? Well, I could drop the factorial, and we could take a look at this. We know 1 over n is the divergent harmonic. All right. Now, 1 over n factorial. Now, again, keep in mind, we're starting at 4. So let's focus down here. Okay. If n is 4, well, 1 over 4 factorial is 1 over 24 versus 1 over 4. Certainly, this is less than or equal to that. If n is 5, right, I got 1 over 120 for the factorial versus 1 over 5. That, again, is less than or equal. Okay. So that's great. I think we showed that n factorial, 1 over n factorial is going to be less than or equal to 1 over n. But does that really help us here? No, just because the larger one diverges doesn't necessarily mean the smaller one does. So instead of 1 over n, let's try to compare instead to 1 over n squared, which now is a convergent p-series. So again, can we make a comparison between these two? Well, let's again take a look. As long as n is equal to 4, right? Here, I'm going to add an n squared column here. So 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Now remember, we're limited to 4 and above here. And I think I see why. Let's take a look. 1 over n factorial. Well, 4 factorial is 24, while 4 squared is 16. That's a larger denominator here, so that would be less. Okay, when I plug in 5, 1 over 5 factorial versus 1 over 5 squared, that again is going to be smaller. If you notice up above the pink line, though, 3 factorial is 6, or 3 squared is 9. Okay, so n squared has the larger denominator above that pink line, which is why that this was indexed where it was. That's all that really means. Okay, but look, don't lose sight of the point of the problem here. Okay, I'm kind of going off on a tangent. Look, what we did is we just showed, kind of again, here's the point that I'm trying to make. We just showed that 1 over n factorial is less than or equal to 1 over n squared for all values of n that we're dealing with in this problem. So again, by the direct comparison test, this thing converges. All right. So again, good practice. This stuff shows up all over the exam, which I hope we're getting ready for. All right. And if you have any questions, shoot me an email. Hope to talk to you guys soon.